Speaker in the afternoon session is Martin Mombelli from Cordoba, and he will tell us about braided commutative algebras.
Okay, thank you. First, I want to thank the organizers, Ms. Vesna, that is not here, but she helped a lot, and to Assad for inviting. So the talk is basically a construction of braided commutative algebras by setting a very complicated categorical structure. And the way I see it is basically you have a finite group and the category of representations of a finite group, and you construct the algebra of characters and the interplay of both theory, how the character algebra helps to understand the category and how it helps to the structure of finite groups. Okay, so first, I will tell you about Davidov full center construction of an algebra. And he starts with a tensor category and an algebra, any algebra in a tensor category. But I have to say first that I will miss a lot of hypotheses and maybe some things I will say wrong, but just to make the talk a bit more digestible. And so for the expert, I will say some things wrong, and maybe for the others, it will give more sense. So the full center of an algebra is a subalgebra of an algebra A here, such that it fulfills some universal property. What the universal property is that this center is universal among all objects that possess some inclusion in the algebra A, and satisfy this inclusion has to satisfy this diagram. And what this diagram is you start here up. So this diagram basically is this equation. So it's like saying that this element belongs to the center. So the missing step here is that you swap elements. The usual swap is changed by the braiding of the category, of the braiding in the Drinfeld center. So this is the definition of Davidov's full center. So later, Shimizu gave another construction of this algebra, but using a different approach. So let's explain this construction. So he started with an exact module category of this tensor category C, via this the rho, the factor, the action factor, and this factor restricts to, when restricted to the center, to the Drinfeld center of the category, then the image of this action factor lands in the category not only factors but C module factors. And he computed an explicit right adjoint of this factor in this way, using the Cohen construction that Chelsea explained already. So there is the right adjoint applied to a factor is some Cohen of some internal home of this object. So every time you have a pair of adjoint factors, it means that there is encoded an algebra there. So this is like in principle a very complicated way to say that there is an algebra. So an algebra is behind a pair of adjoint factors, but the use of this is that sometimes computing a pair of adjoint factors is more easy than computing the algebra itself.
Could you give again the definition of NC of M?
Yes, this is factors from M to M that respect the action of C. It's a C module factors. So of course there is some axiom there, but
Can you maybe remind people, because not everybody is familiar, what is the Drinfeld center? What is that of C?
Okay. So the Drinfeld center of C is another construction related with the Drinfeld, for example, Drinfeld construction of algebra. And the Drinfeld center of C is a category of pairs. Maybe here I can write. So if you have a category C, then the Drinfeld center of C is a category of pairs where X is an object in C, and sigma is a natural isomorphism that behaves like a braiding. It's a half braiding satisfying some natural conditions. So Shimizu's right adjoint, no, not right adjoint, algebra, the adjoint algebra is this right adjoint evaluated in the identity. So let's see, so here, so you have the right adjoint, so you have an element, a distinguished element here that is the identity, and you apply to the identity, and then you get an object in the Drinfeld center that is Shimizu's adjoint algebra. And this is a braided commutative, very special algebra in the Drinfeld center. And okay, I will say something later about this algebra, but I want to show you some examples, some particular example in the case of Hopf algebras. So if H is a finite dimensional Hopf algebra, then so you want to compute some examples, so you need to say what module category of the category of representation of this Hopf algebra. So you take an H comodule algebra, K. So the category of K finite dimensional K modules is a module category of the category of representations of H with action given by the tensor product over the field. So this is the functor action. But then you have to say how K acts on this tensor product, and the action is given by the coaction of K as an H comodule, Turns out that the adjoint algebra in this case has a very explicit description, and you can calculate it as morphisms in this Hom space, such that they satisfy these extra conditions. So in principle, there is a way to compute this algebra at least in some examples.
Martin, what is P?
Sorry, it's K. This is K. Oh. It's not P. So it's H.
BK.
It's a B equals K.
I'm sorry, by your left H commodule algebra, you just require that it's some algebra on the category of the representations of H, which happens to be a left H commodule with no compatibility.
No, K is, yes, as you say, it's an algebra in the category of comodules of H. Oh. So it is a commodule and satisfies an extra condition. Some particular cases of this is when you take K equals H. So the algebra is the adjoint algebra of H that is the same vector space as H and the same product as H, but it has a different H coaction that is given by the adjoint coaction. So here S is the antipode of the Hopf algebra H. And this construction gives a correspondence between exact module categories, indecomposable exact module categories, and commutative, braided commutative algebras in the Drinfeld center with some particularity that it has dimension equal to the dimension of H. And this was proven by Davidov, Müller, Nixich, and Ostrich, that gives, in the semi-simple case, gives a complete invariant of the module category. And for me, since I work here mostly, so for me, this is a very nice invariant of the module category.
Because it is FPDM AM equals FPDM C.
Yeah.
Okay,
dimension of
okay, yeah.
AM, yes, this is the adjoint algebra of M.
But on that left side, inequality, it's FP dimension of the algebra, right?
Yes, it's the dimension of the algebra equals the dimensions of yes, it's the dimension of A. So in some sense, this algebra has the biggest dimension possible. So one could ask what happens with subalgebras of this algebra, and this will be next.
Sorry, so in the semi-simple case, exact would just say I'm looking at semi-simple C module categories, right?
Yes, yes.
And so is this literally something that's specific to the semi-simple one, or are you going to tell me this also holds in the finite case?
It was proven in the semi-simple case. I tried to do it in the non-semi-simple case, and I had some trouble to prove it. I didn't spend too much time doing it, but I think it's true.
Do you assume all the time that your categories are rigid? Do you assume that your categories are rigid?
Yes, they are all finite, abelian, rigid. Yes, all possible. Yes. Yeah. So in a paper in 2021, Lachwitz, it's very difficult to pronounce.
Lachwitz.
Yes. So him and Walton gave a generalization of of Davidoff construction, but not for just a tensor category, but augmented tensor categories. So I will explain what is an augmented tensor category. So you take any braided tensor category, and what Davidoff did was the special case of vector space. So the previous example is with B is the category of vector spaces. So a B central or augmented tensor category is a tensor category C that comes equipped with a faithful monoidal phantom from B to the Drinfeld center of C. And in this case, they gave a very similar definition of the full center. So given an algebra in C, the B center is some algebra in the relative center of C that comes with an inclusion in A and satisfies some universality condition. The universality condition, it's basically the same. Okay, so what I will explain what is a relative center and some examples of augmented tensor categories. So the relative center is there are objects, pair of objects in the Drinfeld center. So here's what I wrote. So they have to have this half braiding, but they have to satisfy that they are sort of transparent with objects that comes from B. So if you think that this object, so if you think that B is the category of vector spaces, so this is like a vector space acting on the units of the tensor category, this equation is trivial because it says that the braiding is additive. So some examples of B central tensor categories or augmented tensor categories are the following. And so the trivial examples is the category of vector spaces included in any finite tensor category, in particular in the Drinfeld center. So if C is braided, there is a canonical inclusion that sends an object to the object, but using the braiding of the original tensor category. Also, if there is a group acting on the category C, there is a canonical braided tensor functor from the category of representation of the finite group into the category of the Drinfeld center of the equivariantization of the tensor category C. And the following example was given by Robert and Walton. And it's the following. You start with a quasi-triangular Hopf algebra T with R matrix given by R. And you take a braided Hopf algebra inside this braided tensor category. And then you can construct the bosonization Hopf algebra H smash T. And this is a usual Hopf algebra. So H is a Hopf algebra inside some braided tensor category. But this is a usual Hopf algebra. And this category is central over the category of representation of T. And the functor from here to the center is just given by, at the level of objects is the identity, but then you have to use some there to give this half braiding on B. So there is another example. If you take any quasi-triangular Hopf algebra and you form the Hopf algebra generated by the first tensorants of R, then Radford proved that there is a morphism from the Drinfeld center of A to H that is a quasi-triangular map. And this gives you a functor from the category of representations of H to the center of this category of A. Usually this Hopf algebra A is called the minimal quasi-triangular Hopf algebra. And this is a very nice example for me. I come from Hopf algebra theory, and it's a very nice example, but spoiler alert, I couldn't do all the calculations that I did with this example. And the main problem that I had is that dimensions, I will say it later, but dimensions in this case are not integers. So it was very difficult to guess what object was, because I couldn't use anything very intuitive.
A is not quasi-triangular though, right?
Yes, it's quasi-triangular.
A is quasi-triangular.
So A is generated by what?
Yes, I'm
What do you
saying
what do you
this
mean by
is,
first tensor?
yes, this is one of the things that I'm saying wrong. It's not only generated by A, the first tensor, but it's a bit more complicated.
So you don't use second tensor component?
Yes, you use the second.
I know, you
Yes.
use both.
Yes,
Multiplies.
yes,
Possible.
more or less, yes. I didn't want to put like the actual definition, but I could, for those that are interested, I could point the paper. It's a Radford paper.
And you say it's quasi-triangular?
Yes, it's quasi-triangular.
Ah, yeah. It has same R matrix, right?
Yes, it's the same. It's
Yes,
like
yes.
taking the
Yes,
minimal
yes.
Hopf algebra such
That
that
is
R
a
belongs to, yeah.
Yeah, but okay.
Yes.
Ah.
And somehow when, okay, I will say later. So what is the generalization of Shimizu's construction in this case? So you take augmented tensor category, a module category over C via this action functor, and you prove that in fact this action functor lands in the category not only of end of functor but B module end of functors. And then you can construct in the same way an adjoint functor to this functor by this formula. So the difference from this formula to the previous used by Shimizu is that I use this contour and that is a bit different for the usual end and coend, because it takes into account how the category B is inside the category C. So this is a bit different, but
Sorry, Martin, I don't see how V is inside C. You just have functor to the Drinfeld center. In what sense V is inside C?
Well, like you have a forgetful functor from the center to C, so you have from B to center to C.
Okay,
So you can see a
So
factor.
you use pullback to make M as a V module.
Yeah. Yes.
You use pullback
Yes.
along this
Exactly.
functor.
Yes. So
Sorry, what was the last statement? Sorry, you're going a bit fast.
so the statement here is that this functor is a right adjoint to this factor. And it looks very similar to the formula of Shimizu. But there is this extra element beta that I call the pre-balancing, that in the case of vector spaces, you deal with functors with additive k-linear functors. So here they are replaced by functors that respect the action of B in some sense.
Can you say more about this coend? Otherwise, we don't understand.
Yes, it's so this coend we wrote with a student of mine a paper because it's an extension of the usual N and coend where there is when you have an enriched tensor category, let's say, so you want to compute an N and coend over an enriched category that takes into account this enrichment. So we did it for other purposes, but it fits very well in here. So again, when you apply this functor to the identity, and since this functor is Lax monoidal functor, it sends algebras to algebras, and then we recover Lauchwig and Walton construction that this is again a commutative braided algebra inside the relative center.
So I'm just confused. From the last slide, it looked like the adjoint would have landed inside of C, not the relative center. Is that?
Well,
so the right you have this right adjoint to this functor rho, then wouldn't that land inside of C rather than the relative center? Or
yes, that's one of the steps that I missed. So in fact, so in principle, it will land here. Of course,
have a canonical central structure for the.
There is a canonical braiding, but the fact that it comes from this coend that respect the action of B, then you can prove it that with a long calculation that it, in fact, is an object in the relative set. And this algebra coincides with the construction of Robert and Walton. And so at last, so we could give an explicit calculation in the case of Hopf algebras, and in the case of the examples of bosonization of Hopf algebras. So as before, if T is a quasi-triangular Hopf algebra, and then you take an H Hopf algebra, a braided Hopf algebra inside that, and then this category is central, and you take a comodule algebra, and then this is a module category of the category of modules of the H, and then we could compute this relative braided commutative algebra, and as before, there are elements in this. Oh, this P is K. Still is K. So with this condition, but now we have an extra condition, and this extra condition is that alpha, it has to be a T comodule map in some sense, which translates into this condition, and here it appears the R matrix of T. And okay, I finished, but I want to say that we couldn't compute this algebra in the case of this. So we couldn't compute this algebra in this case, and for me it would be nice to have it because somehow this algebra would measure how far is a Hopf algebra from being minimal. And as I said before, the problem for computing this algebra was that it has no integer dimension, Frobenius Perron dimension. So it was very difficult to guess what it is. So if you don't have the dimension of this algebra, it's very difficult to compute, because in the other cases, I would guess some very big vector space and I know the dimension, and then I can say, okay, this is the algebra. But since the algebra in this case seems to have non-integer dimension, it was very difficult. But
how bad is the dimension? Is it at least half integers, or
I don't know.
it could be
Yes,
anything.
I don't know, but yeah.
So what do you mean by this algebra? I mean, you take some module category or some commodule algebra over what?
So you take
So it's a central structure, right?
what?
It's a central structure, right? You take module category over rep A.
Yes, you take a module category of rep A,
Some commodule algebra, for example. Okay.
module algebra over A, and then you want to compute this relative adjoint algebra with respect to this.
Rep H. No, it will be what? It will be respect to rep H.
Yes.
Relative to rep H.
Yes. And
But it should be basically object or commutative algebra in relative Greenfield center of rep A, right?
yes.
And what is not, I mean, like explicit formula or?
No, I don't have because these are subalgebras of Shimizu's or Davidov algebras, and remember that this algebra has a particular dimension that is equal to the dimension of the tensor category, and these algebra are subalgebras of this. So you don't have any knowledge of the dimension.
They are subalgebras.
Yes.
Are you saying that this will be subalgebras of the adjoint algebra of M?
Yeah. Somehow these, maybe I'm saying something wrong, but somehow these subalgebras control or enrich. So, and this is one of the things that I want to try to prove, that what happens if you take some subalgebra of Shimizu's adjoint algebra, if you can prove there is some braided tensor category inside the center such that this algebra is an algebra. So there is a correspondence like this, but in the enriched.
But what is this enriched structure? Enriched over what?
Enriched over some braided tensor category
over B.
Yeah.
Enriched over B.
So I wonder if there is this correspondence. First of all, I wonder if this correspondence still is true in the non-semi-simple case. And for example, one of the problems that I had is if a center of a multi-tensor category is trivial, what can you say about this multi-tensor category? And this is one of the problems that I'm having. And also, if this correspondence is still true in this setting. So braided commutative subalgebras inside Shimizu's adjoint algebra corresponds to what? To exact model categories or something. Okay, that's all.
Questions?
So I know you said not semi-simple, but I mean, it's just semi-simple, but let's assume non-semi-simple for a second. So suppose V is just maybe an abelian group, representation of some abelian group, and C is some Nichols algebra. Then basically what you would do is produce for every module category a commutative algebra over the quantum group.
Yes.
And my question, I think, is, so if we have a commutative algebra over the quantum group, we can take modules and local modules, and we get some other categories.
Yes.
So if you do this for C, we get back V, C and V. But if you do it for other module categories, do you ever guess what you get? So you should get a large family of sort of versions of V, but different versions.
Yes, that's the problem that I don't know how to solve it. Yes, exactly.
It's very
And I think when you when you see the proof of David or Muger, you have to go through these transparent modules, local modules, and the theory gets a bit muddy in the non-semi-simple case. If I have time, I want to write it down, but
Maybe dual of C with respect to the module category or something?
I don't know. It's very tricky because in the semi-simple case, when you have an algebra, immediately in a commutative algebra, the modules of an algebra is rigid. But if you take any algebra, it's very difficult to say when, in commutative algebra, it's very difficult to say when the category of modules is rigid. So if it's exact, yes, but if it's not exact,
Exact is
I
fine.
mean, if and if you start with Shimizu's algebra and you take a subalgebra, then to know when it's exact is it's a problem, and so it's non-trivial in the non-semi-simple case. Although you in the proof of them, I mean, you can follow most of the proof.
But do people have lists of commutative algebras of quantum groups? Some paper view or
So in this paper, we wrote an example, a particular example. I think maybe it's the same that Robert and Walton with the Taft algebras, and you take a cyclic group inside the Taft algebra with a non-trivial R matrix. So, and you can, and this formula, you can find explicit algebras.
Sorry, can you say more? Is it related to your last page? In the last example,
Yes.
which was very quick, I didn't get it. And your example is for this last page?
Yes.
This example, right?
Yes.
So it's not about minimal, it's something else. It's about this Booleanization.
Yes, so in some examples, you can compute explicitly all these, you can explicitly compute this Hom space, this Hom of K. This one. So you can compute this space, you can say when this formula, of course, this is the difficult part, but if you have the braiding, maybe the R matrix is somehow nice, you can compute all alpha that satisfies this equation.
But the definition of this algebra, it's like with when I have not, but with the usual adjoint algebra. What's the difference?
These two parts are the adjoint algebra. That's why I put it. So this is the alpha, such that they satisfy this, this, and this. So the first two conditions.
Okay. So that's why it will be smaller, right? Because
Yes.
there is this big, this R matrix condition.
Yeah. Yes.
Right. Yes. And in your example, T was a cyclic group.
Was a cyclic group inside the Taft algebra, and the cyclic group has to have a non-trivial R matrix. So with the
And H you think as a Taft algebra.
yes,
It's like some p-dimensional algebra.
yes, exactly. And T is a cyclic group.
So what are dimensions in this case? In this case, you calculated.
I don't remember, but I could look at the dimensions. But they are all integers. Luckily, in the Hopf case, this is a very particular case of in the Hopf case, and the other case is very different because you see here this is a subalgebra in here, but in the other case it was the other way around. So the sort of smaller category was the bigger Hopf algebra. So that's why it's very difficult to compute.
Can you say more about full center? You started with a full center. What's the relation to the full center?
Well, the full center is equal to was the first construction of this joint algebra. And then Shimizu gave like a different approach. Here. So it's the same as Shimizu's joint algebra, but given a very difficult and a very different way. So at first it's difficult, but then you realize that if you can compute the adjoint factors, then it's easier because you can make a lot of computations with that.
But you mean M is A mod, right?
Yeah.
And full center is A is adjoint
Yes,
algebras.
yes.
And in a relative sense, you have also what will be full center analog of a relative adjoint algebra?
Yes, this is the construction given by Dachwitz and
Okay. Okay. So you tested among not all half braidings, only half braidings from relative center.
yes.
So what is sort of intuition? It's usually bigger than adjoint algebra or smaller?
No, it's a subalgebra of the adjoint algebra.
How
It's
do I-
always a subalgebra.
Hmm.
The bigger the B, the braided category, the smaller is the.
bigger V, smaller is
Yes.
adjoint,
Ah.
relative.
I would guess, for example, if C is already braided, so if C is already braided, so that there is canonical inclusion, then this algebra, I don't know, but maybe it's the trivial one. And this is the biggest example.
Hmm.
More questions?
Since it's not the case, let's thank Martin again. We'll stay with the schedule, like we have 20 minutes break.